All right, we are ready to go. Sorry, it takes me a minute or so to get the YouTube live set up, and now that that's going, we are gonna get started. So, wait, we can't start without my stylus. Here it is. Got it. Okay. So, the first application of what we've been going over with growth and decay is going to be related to half-life. So what we're going to do is we're going to work on the assumption that the rate of decay is proportional to the amount of the material. So hopefully we can recall a little bit about half-life from chemistry, but if not, we'll kind of do a quick overview here. So it says the half-life of some common radioactive isotopes are as follows. So for example, let's start with nobelium, right? The half-life is 23 seconds. So that means, for example, if you have 4 grams of this nobelium, after 23 seconds, you would only have 2 grams because 23 seconds is the half-life, meaning it's going to decay, and after that half-life, you're going to reach that half of the amount that you started with. So let's say maybe you started with 6 grams instead of nobelium. 23 seconds later, you'll only have 3 grams because the half-life is 23 seconds. And then you'll see all the different chemicals have, or isotopes have different half-lives. And so we're going to be using that to answer some questions here. And you'll see we get crazy amounts here of half-lives, from days to years to seconds and all of that. So what that means, we're relating this to the rate of decay. So how quickly things are decaying. Nobelium has a really quick rate of decay, right? 23 seconds, you already have half of it. Whereas radium, it takes 1,620 years to get half of what you started with. So that's a much slower rate of decay than nobelium, for example. Okay. However, it's proportional. We're going off the assumption that it's proportional to the amount of the material. So like, right, we had 4 grams, half of that is 2. We have 6 grams, half of that is 3. So we're maintaining that proportionality. So we're going off that assumption. So example 3 says, suppose that 10 grams of the plutonium isotope Pu-239 was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? So that means we are starting with 10 grams. We want to figure out how long it will take. So that's keyword there, because that's trying to figure out what is T going to be, to go from 10 grams all the way to 1 gram. Okay, so what we need to do, we need to figure out what is our rate that we're using, right? We're going off of the assumption that the rate of decay is proportional to the amount of material. So we're talking about the rate of decay of the material. So what we'll do is we'll say Y is equal to the amount of material. So we know that the rate of decay of that material can be written as dy over dt. So that's the change in y. Y represents the amount of material over time. And then we have the rest of the phrase is, so is meaning equal to, directly proportional to the amount of material. So directly proportional, amount of material is y, so we have k times y. Awesome. So now we have a rate of change that represents this decay. Is that going to help us to figure out how long it will take for the 10 grams to decay to 1 gram? It is going to help us, but not in the form that we have it. We can't do it as a rate. What we need to do is we need to find an equation of y. So that way we can plug in our y value and then get our time as the output. So because of our theorem for decay, growth and decay, we know that y will equal c times e to the kt. This is something that we proved yesterday. Remember when we went through all of that? That gives us the general solution. So there's our general solution, and we've got to figure out what we can do to use the information that they gave us to solve for c and k, because we need to figure that out so that t can be our only variable and y. Let's look at what they told us. We're starting with 10 grams of plutonium. So that means when t is equal to 0, y is equal to 10. That is a piece of information that we can go ahead and plug in to this equation. And this is going to be helpful because k times 0 is 0, e to the 0 is 1. So now we know c is equal to 10. Awesome. So this general equation is going to become a little bit more particular. Come over this way. Y is equal to 10 times e to the k times t. All right. So now we need something else that we can plug in for y and t in order to solve for k. And the problem here is 1 gram is the y value, and its corresponding t is what we're trying to figure out. So we can't really use that 1 at all until the very end when we're trying to solve for t, once we already know what k is. So we still need to figure out what k is. And now we are going to use the information we were given for the half-life here. So we know its half-life is 24,360 years. So I'm going to go ahead and just kind of note that over here. Half-life is 24,360 years. So if we are initially starting with 10 grams, right? When t is equal to 24,360, what is y going to equal? Well, since that's the half-life, that means we're going to have half of what we started with. We started with 10. Now we're going to have 5 grams of the material. So we've just, using the half-life, we actually just created our own set of data that we can plug into this equation. The t value is the half-life, and the y is the corresponding half-life because we know what we started with. So if we know what we started with and we know the half-life, then we know how much material we have at the point of the half-life. So we can plug that in, 5, and then this is going to look really nice. 24,360 times k. And we're going to solve for that k value. So first step is we will need to divide by 10. So that'll give us 5 over 10, which is 1/2. equal to E, 24,360K. To eliminate the E, we need to take ln of both sides. So that goes away. We're left with ln 1/2 is equal to 24,360 times K. And then final step, we divide. So K is equal to ln of 1/2 divided by 24,360. So from here, we have figured out what K is. We have figured out what C is. We can go ahead and plug that into our equation, and then that way we have something that we can actually solve for T now. And I'm going to do a different color here. So Y is equal to 10 times E to the, I'm going to write this, instead of one whole fraction, I'm going to do 1 over 24,360 times ln of 1/2 times T. Why did I write it like that? I don't know. I just felt like it. So now we have this, we just need to solve for T. So T is at the very top of E. So now we are going to have to work our way towards that. Oh wait, I forgot to plug in the Y value, right? Y is equal to 1 gram is what they told us. And we're trying to figure out what is the T value. So here we go. We got to divide by 10. So we have 1/10 is equal to E to the 1 over 24,360 times ln of 1/2 times T. Then we'll take ln of both sides to get rid of that E. So that E goes away. We have ln of 1 over 10 equal to 1 over 24,360 times ln of 1/2 times T. And now to get T on its own, I will need to multiply by this 24,360 and divide by ln of 1/2. So T is going to equal 24,360 times ln of 1 over 10 divided by ln of 1/2. And you can go ahead and plug that into your calculator. It should give you approximately 80.922 years. That doesn't sound right. Is that supposed to be a comma, maybe? Maybe that's supposed to be a comma. I don't have my calculator with me, so we'll have to double check that in a second. But are there any questions on any of that? So the steps are, sorry, I gotta admit someone into the class. The steps are the same as what we did in our example in class yesterday. It's just a matter of this example that we did yesterday has really simplified numbers, right? We're working with 2 and 3 and small little numbers. Whereas here, we've got some bigger numbers, but the steps are still the same. So yeah. Any questions on that? Okay. Then let's jump on to the next problem here. So suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? We're going to round to the nearest fly. So we start out with this sentence here that says that the population increases according to the law of exponential growth. So this is a key phrase as well. We probably haven't seen this yet, I don't think, but this tells us that it follows this rule here, this theorem. So if we can come up with the equation for the rate of change, then we can come up with the general solution, just like we've done in this past problem. So let's see if we can come up with that rate of change equation. What we'll do is we'll let y be the number of flies. Okay. So y is going to represent the number of flies. So we can come up with an equation here, dy over dt, the rate of change of the number of flies over time, is going to be directly proportional to the number of flies, because we know that the fly population increases according to the law of exponential growth. So we can write this and have that be a true statement. Also, that means y is going to have to equal c times e to the kt. Now we're getting somewhere. What we're trying to figure out is how many flies were in the original population. So to begin with, how many flies did we have? And they told us there were 100 flies after the second day and 300 flies after the fourth day. So they're giving us two pieces of information there that we're going to be able to plug in to solve for C and K, so that once we do, we can plug in t equal to 0 and solve for y, because that would mean we are finding the number of flies from the start. Okay, so first thing we're going to have to do is plug in what they've given us. 100 flies after the second day means when t is equal to 2, y is equal to 100. So we can go ahead and use that information. Also, we know 300 flies after the fourth day. So when t is equal to 4, we have y is equal to 300. So we're also going to be using that. So we'll start with this one. 100 is equal to c times e to the k times 2. And we'll solve for either c or k, because in this case nothing cancels out. In the past we've seen k times 0, and so then the k goes away and we've actually just solved for c on its own. In this case, nothing has canceled. So what we're going to do is we're going to solve for c, even if it has k within it, and then we're going to use substitution after that. So let's divide here. So c is going to equal 100 divided by e to the 2k. Okay. Let me know if there's any questions. From here, we know what c is equal to. It's not necessarily an exact answer, but we can take it and plug it in to that C value. So we know it's going to be 100 over e to the 2k times e to the kt. And now we're going to plug in the next piece of information that we know. We know y is going to equal 300 when t is equal to 4. So we have 100 over e to the 2k times e to the 4k. We need to do a little bit of simplifying here. Technically what we have, if I were to kind of rewrite this just a little bit, e to the 4k divided by e to the 2k. And when we're dividing exponentials, we just need to subtract their powers. And we can also divide by this 100. Why not? Let's do it all in one step. So that's going to be 3 equal to e to the 2k. So simplifying as wasn't actually that bad. We need to get rid of e, so we take ln of both sides. That e is gone. So now we have ln of 3 is equal to 2 times k. So k is equal to ln of 3 divided by 2. Now that we know what k is, that's actually a number that you can plug in to your calculator and see what that value is going to be equal to. But we can take that and plug it in for that k. Sorry, I keep forgetting to use the little box so that I can actually write small and make everything fit. Let's see if I can do it here. So the new equation, we have c is 100. Actually, we can plug in this k. Sorry, I forgot that step for a second there. To actually find what c is equal to. So let me do that really quickly here. So this is e to the 2 times ln of 3 divided by 2. And then those 2's are going to cancel out. And then the e and ln cancel out. So we're left with 100 divided by 3. So that's what we're going to use for our c value. And then we have e. Our k was ln 3 over 2. So it's going to be ln 3 over 2 times t. The question, the actual question itself, wants to know what is the initial population. So that means t has to equal 0. So the initial population is actually just that c value, because when t is equal to 0, it makes that whole, excuse me, this becomes 1. So the c value is always going to be that initial population. But nonetheless, there you go. 100 divided by 3 is approximately 33 flies. So that's how many we started with. Those flies sure do duplicate quickly. Any questions on that? Let me know. I'm checking the chat here if you have any questions. Okay. This is the last one that we're going to do, and then I'm going to show you a quick video after this, and the video is pertaining to this Newton's law of cooling. So this question, 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. So we have a decay there. If the sales follow an exponential pattern of decline, what will they be to the nearest unit after another 2 months? So let's go ahead, and we already are being told that the sales are following an exponential pattern of decline. So that's kind of the key word telling us we can use this theorem. We're going to let y be, what is it representing? The number of sales or number of units. Right? So the rate of change of the number of units over time is going to be directly proportional to the number of units. And so y is going to equal c times e to the kt. There we go. All right, so let's go back. We need to try and figure out what c and k is. So let's go back and see what kind of conditions they have given us. To begin with, it says a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. So this means that when time was 0, it started with 100,000 units, right? After 4 months is when it dropped to 80,000 units per month. So sometimes they're going to give you those little clues and you have to kind of piece it together to be able to understand it. So when we're starting, we have 100,000 units. 4 months after that, so when t is equal to 4, our y is going to equal 80,000 units. So there's a decline there. Those are the 2 key points that we're going to be using. You always want to start, if you have an initial condition, use that because it's going to cancel things out nicely for us. So we got 100,000 here. And again, this is just going to give us c is equal to 100,000. So this kind of goes back to what I said earlier. C is going to represent your initial condition. So there we go. We should have known that since we knew initially we had 100,000. But anyways, so now we know C. We need to figure out what K is. So that becomes Y is equal to 100,000 e to the K times T. So next point, Y is 80,000. We've got 100,000 e to the 4K. Since we're plugging in the 4 and the 80,000. So we'll divide by 100,000. That's going to give it simplified to 8 over 10, which is 4/5, equal to e to the 4k. We must take the ln of both sides. So ln of 4/5 is equal to 4k. And then we divide by 4. So k is going to equal ln 4/5 divided by 4. So there is our k value, and we can go ahead and plug both the c and the k in. So y is equal to 100,000 e to the ln of 4/5 t. Now with this equation, we're able to solve for what we really need to solve, and that's after 2 months, what is going to be our number of units. Now, here's something that we need to be careful of. Remember, we start with 0, and then we went 4 months later, right? So After 4 months, we're at 80,000. Now this says after another 2 months, we want to know what's going to be our nearest unit. So am I going to plug in 2 for t? I'm going to plug in 6 because we've already had 4 months go by. Now we want to know after another 2 months, how many units are we going to have? So that keyword is another 2 months, right? Since we're already at 4 months, we already know what happened after 2 months, right? Technically, if you're thinking logically, like if this was a real life situation, why would you need to know? You can just look at the data and see, oh, after 2 months, this is where we're at. But we want to know after another 2 months what we're going to have. So when t is equal to 6, we want to know what y is going to be. So I'm going to plug that in here. And then we are just going to have to plug this into our calculator. And unfortunately, I did not do that yet. So I'm going to do that really quickly on here so we can see the value. And that's going to be 100,000 times e to the ln of 4/5 times 6. And that will equal approximately 26,214.4 to the nearest unit, so 214 units. Here we go. Is k 1/4 times ln? Oh, did I type that? Oh, you're right. Thank you. Good catch. I forgot k has to be divided by 4, so I need to have this 4 here. Let me recalculate this. Okay. I was just about to check and see, does this, sometimes you got to see, does your answer make sense, right? 71,554 units. And so we started with 100,000 units per month. After 4 months, it went down to 80,000 units. And then after another 2 months, it went down to 71,554 units. That makes sense, right? Originally, I had, what did I say, 26,000? So if we think about it, would that totally make sense for you to go from 80,000 units and then 2 months later drastically down to 26,000? I wouldn't think so, right? It would be a really, really drastic decline. So 71,000 does sound more reasonable. So that's just another reason why make sure you always check your work. You guys know I make mistakes sometimes, so it's good to double check that. Anything else? Any other questions or things maybe I missed? Okay. So those are just a few examples of where this rate growth and decay can be applied to in real life. There's a whole lot of different situations where we have that kind of direct proportionality and rate of growth and decay, which we'll see some more examples. But I want to show a video to you all that has to do with Newton's law of cooling. So it's going to go through what this theorem is and kind of break it down for you. And hopefully you guys enjoy it. So I'm going to stop sharing this screen and share another screen with you all. And if I can find it. Sorry, give me a second here. Ooh. Okay, let's see if this works. I feel like that's just what I'm always saying. Okay. Question, do you all see me in black and white? Is that what you're seeing on your screens right now? Yes. Awesome. Okay. Cool. So here we go. Enjoy the video. It's a little bit old, so you may see my hair looks different, but enjoy the show. Here we see Miss Martin working long, hard hours trying to get all of her grading done for her wonderful students. All of that hard work is starting to make her a little bit sleepy. When she wakes up from her nap, there's only one thing on her mind. Coffee. Miss Martin can't drink coffee unless it's in her I ate some pie and it was delicious mug. Uh-oh, she got burnt. Have you ever wondered how long you should have waited before taking a first sip out of your coffee instead of getting burned like Miss Martin just did? Well, now Miss Martin is going to help us figure this out using good old calculus.
So this is the perfect opportunity for us to use Newton's law of cooling. So Newton's law of cooling says the rate of change of an object is proportional to the difference between its own temperature and its surrounding temperature. So let's see if we can write an equation out of this definition here. We see the first phrase says the rate of change of an object. So how do we write rate of change? Well, rate of change is the same thing as a derivative. So we're going to write dt over dt. So how did I come up with that? Well, we see at the top here, this capital T stands for temperature. So this is the change in temperature over the change in time. So the rate of change of an object is dt over dt. Then we see the word is. So the rate of change is, whenever we see that, we want to write equals. So it is proportional to the difference. So when we see proportional, that just means we are multiplying by a constant. So I'm going to use just the letter K as a constant. And it's proportional to the difference. So when we see difference, we know it's going to have to be subtraction between its own temperature and its surrounding temperature. So I'm going to use capital T to represent temperature, the object's temperature, just like we used capital T here to represent the change in the object's temperature. So this is the temperature, change in temperature, and then we're going to subtract the surrounding temperature. So I'm going to use capital T again with a little s there to represent surrounding temperature. So this is the equation that represents Newton's law of cooling. So now we have our equation for the rate of change based off of Newton's law of cooling. I did make sure to put a negative here because it is the law of cooling. So that means that we want to have a rate of change that is negative because it's going to be decreasing. And so what we have here is called the differential equation because it really is a derivative of the temperature. In order for us to solve for the original equation of this temperature, we're going to need to integrate this because integration is the opposite of derivatives. If we have a derivative here, we're going to have to integrate it to get the original solution and get the general solution is what we call it. General solution is what we're looking for. Okay, so what we need to do is use the strategy of separation of variables. We see here we have the variable for T, and we have capital T for temperature, and we have the variable for lowercase t for the time. So what I want to do is move over here where I see this capital T. I'm going to move this over by dividing to the other side to get it together with this capital T that I see here. And I'm going to move this d over t over to the right side by multiplying it over so that we can then separate these two variables. So dividing by t minus t sub s, we're going to get 1 over t minus t sub s on the left side times dt, because this dt is not moving. The negative k is also going to be staying, but we're multiplying by dt to the other side, so we have negative k times dt. Now that we've separated the variables, we can actually integrate. So we'll integrate both sides. This right here reminds me of the integral of 1 over u, so it's a u substitution. The integral of 1 over u is equal to ln absolute value of u. So I can go over here and I know that this integral is going to be ln absolute value of whatever is down here, which is t minus t sub s. The dt goes away because we've integrated, so the integral goes away, the dt goes away. Normally we add the constant, but since we're still going to be integrating on that side, we'll add the constant to the other side. The integral of any constant is the constant times the variable here. So the variable is t, so this integral is going to be negative k times t, and now we're going to go ahead and add our constant there. We want to be able to solve for t, so first of all we want to think about these absolute values here. This t represents the temperature of my coffee, and this t sub s represents the temperature of the room. So I know that my coffee is hotter than the room, so if we have the temperature of my coffee minus the room temperature, it's still going to be positive. So we can go ahead and get rid of those absolute values because we know that they're always going to be positive, so we don't need them there. And we want to solve for t, so to get rid of ln, we're going to take e of both sides. So now this whole thing becomes our exponent to e, and e is our base. And same thing here, except e now cancels ln, so we're left with t minus t sub s. On this side, e to the negative kt plus c is the same thing as e to the negative kt times e to the c. E to the c is just going to be a constant, so we can replace that with a c. Really, this just becomes c times e to the negative kt. The last thing we want to do to be able to solve for t is add this t sub s to the other side. So t equals c times e to the negative kt plus t sub s. Alright, so now that we have the equation for temperature, we can start to kind of look at its different parts and see how it fits in with the problem. So of course, capital T stands for temperature of my coffee. C is a constant which we got from the integral, and k is another constant, so we're going to have to solve for these constants in a bit. And then we have lowercase t, which stands for time, and uppercase T sub s stands for the temperature of the surrounding area. So in this case, the temperature of my house, which at this point is 74 degrees, or at least at the time where I made my coffee. So here we see a chart where at time equals 0, I checked the temperature and it was 160 degrees. And at that point I took a sip and of course it burned my tongue. So I want to figure out how long it'll take for the temperature to go down to about 135 degrees. I saw online that 140 degrees is about the average temperature for a drink, but after that burn, I want to make sure that I don't burn myself again, so I want to take a sip once it goes down to 135 degrees Fahrenheit. So after 2 minutes, I saw that the temperature went down just 5 degrees Fahrenheit to 155 degrees. So instead of waiting it out, I decided let's use Newton's law and see what we can come up with the time will be for me to finally take my next sip without burning myself. So what we want to do is start out with this initial information where t equals 0, lowercase t equals 0, and uppercase t equals 160 degrees. So we have our uppercase t and our lowercase t there, which we will plug in. So 160 equals c e to the negative k times 0, and we're also going to plug in 74 degrees there. Anything times 0 is going to give us 0. E to the 0 power is just going to be 1. 1 times c is just going to give us c. So to solve for c, which we said we needed to figure out that constant, we're just going to subtract 74 to the other side. So 160 minus 74 gives us 86. So we now know that this constant is 86, and we can plug it into our general solution here. So our new equation is t equals 86 e to the negative kt plus 74. We're going to keep that plugged in there. Okay. The next step is we need to figure out what this k constant is. So we'll use the next information. If we plug in 0 again, it's going to make this k go away because 0 times k is going to become 0. So we don't want to use this information anymore. We're going to move on to plug in 2 and 155 degrees, and then we'll solve for k that way. And we'll find out that k is equal to ln of 155 minus 74, all divided by 86, and all divided by negative 2. So this would approximately be 0.0299, and that will be our value for k, which we will then plug in here. So as of now, we have t of s, which is 74 degrees. We have figured out what k is, and we have also figured out what our c is. So let's write out what our equation now looks like. We have t equals 86 e to the negative 0.0299, that was our k, times t plus 74. This is now our equation for temperature, so we can plug in any temperature and solve for t, which is time, or we could plug in any time and figure out what the temperature will be at that time. My goal is to figure out how long will it take for me to finally take a sip when the coffee reaches 135 degrees. So I'm going to take 135 degrees, plug that in for my t, and I will need to solve for that t value there. Once I finally solve for this t, we will find out that T is equal to approximately 11.46 minutes. So that tells me that from the time that I made my coffee, I should wait about 11 minutes before I take my sip, because otherwise I might end up burned.
All right, so there you are. There was the Newton's law of cooling. I hope you enjoyed it. I hope they make sense. On Friday, we will start with Newton's law of cooling and kind of talk about it a little bit more. But I'll also link this video for you to go back on your own and look at it again so that you can get a better understanding. Hopefully, by the time class comes around on Friday, we can just work on some examples. So for homework, I am going to be posting some problems from the book. They're going to be problems similar to the ones that we did in class today. So if you need to come back to this video on YouTube, feel free to do so. Let me know if you have any questions. I'll be available for the regular tutoring times. If you just check the school schedule, then you can see when that would be. Other than that, I hope you all have a great day. Let me know if you have any questions or anything. But class is now over, so I'll see you all on Friday, if not sooner.